This is the video 2 for the kinematics unit. So in this one, let's talk about what happens if a displacement versus time graph, if there's no straight lines on it. How do we interpret slope with something that doesn't appear to have any slopes? So here I have a graph. It's a position versus time graph, and we can see that it's a pretty long curve. So when you don't see any noticeable slopes, then the slope of a tangent line will be the velocity at that instant in time. So looking at this curve, we can see that there's several different tangent lines we could draw. I could have one right here. Now notice that this is a positive slope, so we see that we have a positive velocity at this instant in time. Up here at the very top, notice that the slope would be 0. So there, the velocity would be 0. So at that moment in time, the object has stopped moving. If I look at a line in between here, we notice that it's still positive, but its slope is less than this first one I drew. So we see that the object is slowing down as it reaches, looks like 2 seconds. At 2 seconds, its instantaneous velocity is 0. At a point right here, we see that we have a negative slope. So that means that the object is traveling again, but it's traveling in a negative direction. So again, we call these instantaneous velocities. These are velocities at specific instances in time. And we could, if you think about it, there's an infinite number of velocities we could find here. So sometimes we may be interested in that instantaneous velocity instead of the velocity for an entire trip. The way we calculate it is to use a limit. So the instantaneous velocity equals the limit as time approaches some number of delta x over delta t. This does lead us into calculus and something called the derivative. Velocity equals the derivative of the position function with respect to time. And if you think about it, what we've done is we've just changed our deltas into d's. So our triangles become d's. That's really the bridge between algebra physics and calculus physics. So those of you taking calculus, you'll appreciate this pretty soon. So let me show off a little bit here. Let's say we have a function x equals 2 plus 3t cubed. What is the instantaneous velocity at a time of 2 seconds? So looking at this, we see that we have a t cubed, so that's an S-curve kind of a graph. So it's definitely something that's kind of has a shape. So to do the derivative, let's rewrite this equation. The derivative is kind of a command. I command thee to take the derivative. So we're going to go through and we're going to derive this. So the derivative dx dt for this function, well, first off, the derivative of a constant, so like a number, like number 2, would be 0. And then to find the derivative of 3t cubed, you take the exponent and you multiply it by the coefficient. So 3 times 3 is 9. And then you subtract 1 off of the exponent. So 3 minus 1 equals 2. So that means then that the velocity, because dx dt is velocity, will equal 9t squared. And at 2 seconds, the velocity would equal 9 times 2 squared. So that is 9 times 4, so At 2 seconds, it's 36 meters per second. All right, so that's one way we can use some calculus in physics. And again, this isn't something I'd ask you to do for me, but I like to show it to you, especially since some of you are taking calculus. All right, moving on then, acceleration. If we have a constant acceleration, this is a nice even change in the velocity over time. So let's say I have something that has an acceleration of 4 meters per second, or again, that's like meters per second squared. Its initial velocity, v naught, is 0 meters per second. So what that means then is at 0 seconds, the object is traveling at 0 meters per second. After 1 second, it is now traveling at 4 meters per second. After 2 seconds, it's now traveling at 8. And we can just keep going. So the velocity will continue to increase, forever, theoretically. So let's go make a graph of this. Again, we're going to place time on the x-axis. So I've got from 0 to 5 seconds. This is a 20 by 20 grid. So I think I need to have 4 spaces in between. Nope, I got that messed up. Can't count. 1, 2, 3, 4. There we go. On the y-axis, we'll put our velocities, measured in meters per second. The top velocity is 20 meters per second. It's a 20 by 20 grid, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now all we need to do is go ahead and graph our data points. So at 0, got 0. 4, 5, 6, 7, 8. So there we have it. Now, notice that this is a nice linear line. So again, I'm going to freehand this. I want you to use some sort of straight edge, a book or something, to give yourself a nice clean line through this. Yeah, I don't like that. That's a little better. Okay, now since this is a linear line, let's go ahead and let's think about what the slope would represent and what the area would represent. The slope, which is rise over run, so that would be meters per second divided by second, so meters per second per second. So we see then that the slope of this line then should give us acceleration. The area under this line, well, area is like a length times a width, so the area, it would be meters per second times second, so meter per second times second will give me meter. So the area underneath this would give me displacement, not distance, but displacement. So in this case, both slope and area have meaning. So let's go ahead and calculate the slope of this line. Again, do not choose data points. This looks pretty close down here. I'll choose that point. And yeah, that one looks pretty good. I'll choose that point up there. It won't be perfect, but it'll be close. All right, so slope, change in y over change in x. So here I've got 20 meters per second minus, down here I've got 2 meters per second. Here the time, see this is 0.25, 0.5, 0.7, so 4.75. seconds minus down here I get 0.5. So the slope, if I do that, it's going to be what, 18 over 4.25. So let me grab my calculator. And I'm getting like, 4.2 meters per second per second. So again, it should have been 4 meters per second, but I freehanded this. If you do this on your own, I think you'll find that you get really, really close to 4. So what this means then is that acceleration, since it's y2 minus y1, it's going to be final velocity minus initial velocity divided by final time minus initial time. So the acceleration equals delta v over delta t. It is a vector because velocity is a vector. We can play around with this formula just a little bit. I like to rewrite this like this. Final velocity equals initial velocity plus acceleration multiplied by time. I like to do it like that. Oftentimes your initial time, t naught, will equal 0. So that kind of gets rid of that delta for you. And that just, I don't know, I kind of like that a little bit better. All right, so again, for this one, slope means acceleration. Area, so that's all this stuff down here, means displacement. So notice then that slope means two different things depending on the graph. So the last graph we saw was a position versus time graph, and there the slope meant velocity. And here we have an acceleration versus time graph. I'm sorry, a velocity versus time graph. So slope means acceleration. All right, this will conclude video 2.